Welcome to Observatory Night. I'm Christine. I will be your host for the evening. Tonight's speaker, Dr. Martin Elvis, has worked with one of NASA's great observatories, the Chandra X-ray Observatory, for 16 years. He has spent his entire career, there's the Chandra X-ray Observatory, he spent his entire career studying active galactic nuclei and quasars, which are powered by supermassive black holes at the centers of galaxies. Amazingly bright objects pour out huge amounts of X-rays and everything else too. And because of all of this work, Martin knows the value of these space observatories. Now, the problem is that the next generation of space telescopes are actually being threatened. They might not even be built. And the reason for that is that they have grown so expensive. I mean, just to take one example, the James Webb Space Telescope. When it was first proposed, first designed, it was going to be a $1 billion telescope. Now the costs have ballooned up to $9 billion and could still be growing. It's because of that it was actually threatened with cancellation just last year. And with costs growing that high, you can only afford to put up maybe one of these space observatories every decade or two, which is just not enough to answer all of the questions that we want to ask about the universe. So that's the problem. Is there a solution? Martin Elvis believes that there is, and that the secret will actually be found by harnessing the asteroids. It doesn't seem like the two are connected, but they actually are. And he is going to be telling us how, by developing this asteroid quest and harnessing the asteroids, we may actually be able to lead to a new fleet of great observatories. So, please welcome Dr. Martin Elvis.
Okay, thank you, Christine. Yes, last time I gave this, it was at this talk, a much primitive version of it, at the Air and Space Museum, at the Planetarium on the Mall in Washington, and I had to compete with recorded Robert Redford. That was pretty tricky, but I thought this would be much easier, but now Christine's gone and made it difficult by showing you those beautiful movies. I just don't get a break, right? Okay. So, NASA has plans to go to the asteroids. And whenever I tell people about this excitedly, I always get the reaction, why? Well, why do we do anything? And the list in my title covers much of what drives us. Love, fear, and greed are each great motivators. And all three are working together when we think about going to the asteroids. So the first, a disclaimer. As Christine said, I spent decades researching quasars and supermassive black holes at the very edge of the universe. And visiting the asteroids is a new obsession of mine, new passion of mine, and so I'm still on the learning curve, and it's a little hard for me to focus on things that close. Right? So first, what are the asteroids? Well, asteroids are rocks in space. Here are some images of them. Flying mountains. But why are there flying mountains in space? This seems a very strange thing. Basically, asteroids are the floor sweepings left over after the main planets of the solar system formed. Now, you know that the 8 major planets of the solar system move around their orbits in grand isolation, not interfering with one another, thank goodness. And this is not by chance. The planets formed from a giant disk of cold gas, called the pre-solar nebula. And this is a Hubble image of 4 young stars with nebulae like that around them. And they can see them as shadows against the glow of the Orion Nebula. You just saw a picture of the Orion Nebula from Spitzer. And over time, and of course, of just a few million years, if astronomers speak, just a few million is just nothing, right? They condensed and clumped up due to gravity and grew into small protoplanets called planetesimals. And these were strewn at random at first in a disk circling the sun, orbiting the sun. And so naturally they had collisions, and they either combined into larger and larger globes, or they got split up and made smaller. And eventually, these collisions led to just a few giant planets, each one cleaning out all the debris from its ring around its orbit. And of course, if any one of them had been too close to, any pair of them had been too close together, they'd have pulled on each other with gravity, and one of them would have been ejected, and they wouldn't have stayed around for the 4.5 billion years that the planets have stayed around. So that's why the planets are so far apart, and why it takes a long time to get to them. But There's one place not far away from us where this process stalled. Just outside the orbit of Mars, shown in orange there in the middle, is a region where Jupiter, which is the largest planet, of course, stopped these planetesimals from merging together. And instead, then, they had to continue just banging together and being broken into smaller and smaller pieces. So we're left with a debris field, which are the asteroids. Something terrible has happened over there. Oh, well. I shall continue ignoring it. And you end up with many of the asteroids looking like just rubble piles of just rock held together by their very weak gravity, microgravity. Like this is a Itokawa, taken in a close-up taken by the Japanese spacecraft Hayabusa. So asteroids even continue to collide today. Just a couple of years ago, Hubble took this image of two asteroids colliding. Now, some of the asteroids from the main belt get deflected by Jupiter or Mars and fall into the inner solar system. And a few have orbits that cross the orbit of the Earth, and these are called the near-Earth asteroids, which are mainly the ones I'm going to talk about tonight. They're shown in red here. Their orbits cross the Earth's orbit. Again, when I say a few, this is astronomer speak. There are actually about 20,000 of them that are bigger than the size of a football stadium, about 100 meters diameter. Although we've only found about 10% of them so far. Just to complete the picture, occasionally dust from one of these asteroids enters through the atmosphere, and we see them as shooting stars, meteors, a meteor shower. This is a beautiful picture of the Leonids I found on the web. And then occasionally somewhat larger chunks actually reach the ground, and where we call them meteorites. And the Smithsonian's Museum of Natural History in Washington has the world's largest collection, about 20,000 of them. So, there are millions of asteroids, and their history and their future lead us to all three of the great motivators, love, fear, and greed. And I'll take each one in turn. Love. Now, to quickly disappoint you, in English, love is a very broad term, covering romantic love, but also love of your kids, of your parents, if your parents are very lucky, of football teams, and much more. And the love I'm talking about is, of course, the love of knowledge, the love of finding things out. We are all curious, and scientists like me are very lucky. We get paid to be curious. But asteroids are just lumps of rock. That's not very interesting. How can it be even interesting to a scientist? Well, in fact, they're a lot more than that. In the last few years, asteroids have been implicated in really big questions. Are there materials in space that cannot be made on Earth? Did gold mines come from asteroids? Where did the oceans come from, and how did life start? Let's start with the exotic materials. Asteroids are kind of natural experiments in material science in a couple of ways. First, we can duplicate the vacuum of space and the colder space in the laboratory, and at the International Space Station, we can even duplicate zero-G, or milli-G anyway. But we cannot duplicate the 10 million years that the pre-solar nebula had to see if exotic molecules and crystals go very delicately and slowly. And perhaps some of those will have strange new properties. It's very difficult to get a 10 million year grant, I can tell you. Origins of life. If you take the molecular ingredients found in those water-rich asteroids, you find they're also carbon-rich. And then if you mix those up under the right conditions, you make complex organic molecules. And this actually happens in space. This is a fragment of the Murchison meteorite, which contains enormous amounts of these organic materials. In fact, if you slice a new piece off and sniff it, it smells like asphalt or tar. So these are all pretty big questions, and I didn't even include the origin of the solar system, which is where most asteroid scientists would begin. In the 20th century, there have been at least one, probably two asteroids as large as the one that made the Arizona meteor crater, and they devastated large areas. This appeared in a newspaper in 1930, just actually after 1930, reporting an impact in the Brazilian Amazon region, Rio Curaçá, near the Peruvian border, extremely remote area, especially at that time. There is now evidence for a very faint evidence for a very faint 1 kilometer across crater seen under the jungle there, which of course has regrown since. So, Details are sparse, but it does make you wonder if these impacts are really so rare as we had thought. There's no guarantee, in fact, that we won't be hit by something really big. The dinosaurs, famously, were wiped out by an asteroid, the Chicxulub impact. Now, the evidence for that comes from this iridium layer, a thin layer of rock found worldwide at the junction between the Cretaceous and the Tertiary. And below there, dinosaurs. Above, bad news for dinosaurs. Luckily, there aren't many asteroids of this size, right? That was a 10-kilometer across, 6-mile across asteroid that made that hole. And Congress got worried about this and told NASA to go search for it back in 2005. So NASA sponsored several searches for big asteroids, and they found 90% of the really big ones, more than a kilometer across. And they know that none of these are a threat for now, for the next century or so, right? But some are still being found, and there could be some lurking behind the sun on orbits that only bring them slowly towards the Earth, and we may only see those when it's too late. But we don't have to gamble. We can just go out and find all the rocks and check their orbits and see if they're going to hit us or not. And if any do turn out to be dangerous, we can just tag and tow them. Now, tagging a giant rock in space sounds easy, relatively. But how do you tow a flying mountain, right? Now, there's one way, which is nuclear bombs. Now, Bruce Willis's character was ever so brave, and it was a touching moment when he blew himself up. Oh, I blew it. I'm sorry. Spoiler alert. But he made the mistake of drilling deep into the asteroid and setting off his bomb somewhere in the middle and blowing it apart. That doesn't really help at all. The pieces are all still on the same orbit, and they will all hit the Earth still. A bomb set off to one side might be much better. It could just nudge the asteroid off course, unless, of course, it blows the asteroid to pieces. So it doesn't work on those rubble piles at all. Well, there is another way. We could use a gravity tractor. And this is not some Star Trek device like a tractor beam. This is just, you just put the biggest mass you can off to one side of the asteroid and pull on it with gravity. Now, that's a very slow process. So you need lots of warning time. You can change the asteroid's speed by about 1/10 of a mile an hour per year. This is not Ferrari standards. But it's very reliable. It works on any kind of asteroid at all. You just have to be sure that those jets that you see there are not pointing back at the asteroid to counteract the pull, which would be really sad. So the trick then is to first find the asteroids and get to them early enough that we can use this very reliable method. So how do we do that? We have to be clever in a couple of ways. The first one is to send up a thermal infrared detecting telescope. Now, everything emits at some light, depending on its temperature, and it could be optical light, and that would be like the sun, which is very hot, or infrared light from something cooler, like a person. And this is Ned Wright, who is the principal investigator of NASA's WISE mission, which was an infrared survey of the sky. He's about the same temperature as a near-Earth asteroid, and so are you. And this is taken from one of the cameras later installed on his small telescope. Very small, you see. When you point that at the sky with the right camera, the near-Earth asteroids show up beautifully as that little red dot is a different color from the stars and galaxies around it. And you can also see it move, so you can track its orbit and find out whether it's going to be dangerous, whether it's going to hit us or not. WISE managed to find about 400 near-Earth asteroids, which isn't many out of the total that are seen, but because they'd made a very careful survey, they could extrapolate and work out how many there must be out there. So the ones that are known are seen in beige, the ones they predict to be there, also, but not yet seen, are in green, and luckily the number is less than the number we expected beforehand, which is the whole thing here on the right. Each one of these little mini rocks represents 100 asteroids. Okay, but still, you can see that in the football field diameter here, football stadium sized or bigger, there's still 90% of them not yet found. So how do we find them? Especially those ones hiding behind the sun, which is really, really annoying. So this is a little bit of a complicated graph. This is a picture of the solar system with the yellow sun in the center going out to the Earth's orbit, and the blue and red dots are the near-Earth asteroids. Okay, so that's the Earth. And now you know that you can only see with a telescope on the night side. That's why you have this thing in the evening here, so you can go observing, and that means you look outwards, away from the sun. But as you can see, most of the near-Earth asteroids at any time are on the other side, on the sunlit side. So any telescope based on Earth can see maybe a little bit into the other side, but not very far. Okay? So this is where we need our trick number 2. As Kepler taught us, the closer in planets move faster around in their orbits. So if we put a telescope in an orbit around the sun similar to Venus, looking outwards, it can look anywhere that's Venus's orbit. And there's a satellite in a Venus-like orbit. It's able to look out, first of all, it can look at a much bigger piece of the Earth's orbit and pick up many more of those near-Earth asteroids. But even better, because it moves around the sun quicker, it can later look behind the sun and at those that are still lurking out there, moving only slowly towards us. So it can map out the entire population down to those even smaller than a football stadium. So that's most of the city killers that we've taken care of. Great, easy. The bad news is that right now, this telescope is just an idea. It's been worked out in quite great detail, but it's too expensive for NASA. And that gets us to greed. Now, my bet is that you're most intrigued about this of the 3 things in my title, because space and greed don't often turn up in the same sentence. I think they should. As Christine said, I'm an astronomer and I really care about bringing down the cost of the great observatories. Right now we're very, very lucky. We have access to 3 great observatories, Hubble, Chandra and Spitzer, and together they span a huge chunk of the electromagnetic spectrum and they show us wonders. And importantly, having them all at once allows us to make connections across the spectrum and fill in different parts of the puzzle that these objects in the sky set us. The image of this nearby galaxy shows each telescope image in a different color. So green is Hubble, blue is Chandra, X-rays, and red is Spitzer, infrared. And each image is quite different. You would never guess from one of them what the other one looked like. But together, the jigsaw fits together and makes a beautiful physics story. There's the sudden burst of bright young stars in the center of the galaxy, and it's blowing a hot wind out of the nucleus. But the great observatories are aging. The youngest is 12 years old. And sometime in the next decade, we will surely lose one or more. Now, NASA, as Christine said, is working on the James Webb Space Telescope, which is a replacement. And it will be as huge a step as Hubble or the other great observatories. And it's great, but we can only afford one of them. And so parts of the spectrum will drop away. We will go blind in certain eyes that we now have. And making these unexpected connections and understanding what's up there will just not be as easy in the James Webb era. So what can we do? Well, if only it were cheaper to get things into space, we could build cheaper observatories so we could afford a full set. Now, how's that looking? Okay, there's Apollo 11, 1969. The Apollo rockets, Saturn V rockets, put tonnage into orbit at a cost, in today's dollars, of around $20,000 a kilogram. $9,000 a pound. That's quite a high cargo rate. And after 50 years of the space program, the cost of launching to orbit today is $20,000 a kilogram. After 50 years, there's no cost reduction. This is not what you see in computers or in many other fields. Why? The bad effect of this can be seen by comparing the global space industry with, say, Walmart. It's not a big industry, and it's been kept small because nobody can afford those kind of cargo rates. Federal Express would not go very far at that rate. How can we get to space cheaper? Everybody thinks space is inherently expensive. It is not. One of SpaceX's new Falcon 9 rockets costs about $50 million to launch, which is a bargain by rates charged by others. Now, here's the good question. I won't be able to see too easily, but how much of that $50 million do you think is fuel? Anyone want to venture a guess? Oh, you were the only person to guess too low. I've asked that. That's really... Oh. Okay, I'll tell you the right answer. I usually get guesses like $1 million or 20 million or something like that. And you're much closer, really. It's $200,000. You can work that out just from the volume of, you estimate the volume of it and multiply by the price of gasoline, and you come out with about the right number. And that's Elon Musk, who founded SpaceX, standing there, and he came up with that number, so I believe him. So that tells you that the cost of launching something into space could go down 10 times, and the cost of the fuel would not be important, even 100 times, and the fuel would only start to begin to be important. Okay, so it's not inherently expensive. And it isn't even that we need some revolutionary new technology. Now, anyone see Mad Men? Because Don Draper in that TV series set in the early 60s went from New York to LA in one episode, and it was a very big deal, very exciting for people, because no one went to California just for business, because it was so expensive. Back then, his ticket cost easily 10 times what it would cost you today, right? But that was the same airplane, the airplane technology was the same jet engines that we use today, essentially, but they've been refined incrementally over the years and brought down the cost a lot, and that's been driven by competition. So what we need is some incentive to bring launch costs down, and I think there's really only one way. Greed. Greed provides the counterweight to caution. Profit is the check that balances the tendency for costs to just keep growing out of control. A NASA engineer or a military designer has no particular reason to cut costs. They have no incentive to do so. But if you're in a commercial enterprise, it really matters. Well, how can you make a profit from space? Tourism, that's a good start. This is the Virgin 2 spaceship. Spaceship 2, the Virgin Galactic spaceship, which should start carrying passengers on 15-minute suborbital rides at the end of this year. If you have $200,000, you can go. You're behind about 300 people in the queue, but there you go. If you pay up front the full $200,000, you can get further up on in the queue. If you just put down a deposit, they put you near the end. So it's clever pricing, just like the airlines, right? But it's a long way from one of these little suborbital hops, even to a low Earth orbit. Now, the only other way I know to make money from space, potentially, is by asteroid mining. Asteroid mining would do much more to increase our capabilities in space and will take us well away from the low Earth orbit out into the solar system. Now, there are lots of ideas for how to mine resources in space, and John Lewis wrote this book, Mining the Sky, which catalogues the vast resources of the solar system. And there's quite a lot of scholarly papers around that go into the details. But, like me, these people are all scientists, and we don't normally think about profit. We kind of assume that if you have vast resources in the sky, then space is profitable. The problem is that in space, not only is there no one to hear you scream, there's no one to sell anything to. It's a clear case of pie in the sky. Oh, sorry about that. Right now, asteroid mining would not make a profit. To get space mining going, we need to find one thing that makes a profit, preferably an obscene profit, back here on Earth, right from the get-go, some kind of pump primer. And that means finding something we can bring back that is worth a lot more than that high launch cost to go get it. Can we find such a thing? The answer is a resounding yes, but. The right asteroids contain one thing in abundance relative to Earth, and that's platinum and platinum group metals. Platinum's 30 times rarer than gold. Its price fluctuates. Right now it's around $60,000 for a kilo. That's 3 times the launch cost. So if a 1-ton mining robot could go out and bring back 10 tons of platinum, we'd make a cool $580 million. That's, however, still a scientist talking. We have to subtract out the substantial cost of building that robot, operating it, and don't forget the interest on the loan we have to take out to do so, right? Still, it's a promising start to a business case. But why go to get platinum in space? Why not just mine it on Earth like we do? Well, remember that late bombardment of asteroids that enriched the surface of the Earth? The platinum that came from the asteroids got diluted in the local rock by a lot. Now, although some of it has been distilled back to pure ore by the action of heat and water, the platinum group metal content of the richest meteorites is still 5 times that of the richest platinum mines on Earth. So that's promising. In fact, if you take one of the smallest platinum-rich asteroids that we could easily find with our telescopes, it would be about, say, 200 meters diameter, it would contain about $35 billion worth of platinum.
That's a bit smaller than Bill Gates's fortune. It's about the size of the Harvard endowment, so around here we think that's pretty significant. It's almost 2 years of production from conventional mining here on Earth, so encouraging. And now, once one mission makes a profit, there'll be a platinum rush to space, and as the low-hanging fruit is mined out, the less ore-rich or harder to get to asteroids will become the targets. And the initial profits be used to push down launch costs so that these become profitable too. And then mining itself will create a market for resources in space. And rocket fuel, for instance, water from these carbonaceous asteroids I was so keen on earlier for science, for example, can be sold to the mining companies. And the space economy will start growing. But, we get to the but. But no venture capitalist right now is going to put down about $5 billion, even to get $35 billion back, because it will take at least 10 years. It's not that $5 billion is too much. Mining companies regularly invest that kind of large sum. It's that the risks are too high and the time scale is too long. So, how can we get started? I suggest we take a lesson from the opening up of the American West to settlers. Now, brave and bold as these guys surely were, braver than me, that's certain, the miners and farmers setting off from Independence, Missouri in their Conestoga wagons were not setting off into unknown land. It's not widely appreciated, but the US government invested heavily and long-term in the opening of the West. The government had mapped out the territory for the pioneers, located resources, water, mineral, and they'd reduced the hazards, which is a euphemism that we won't need to apply in space. It began with Thomas Jefferson sending out Lewis and Clark in 1804 and continued all the way through subsidizing the transcontinental railroad 60 years later. That's something where the government has a good track record. So what could the government do to bring down, to promote the mining of asteroids? We need a practical program of particular steps. Let me outline some. They fall into 4 groups. There's exploration, resource extraction, legal and diplomatic, and economics and marketing. So, first the NASA steps, the technological stuff. There's a whole lot of things we could do. And interestingly, they're pretty much the same as you'd do to send humans to an asteroid, at least to begin with. So the first thing is, let's just do this mission, right? First, find all the rocks. The survey for the killer asteroids would also find all the other mineable asteroids. We'd have to follow it up with a specialized telescope to find out what they're made of, just a small number of them. And then, once we've got really good ones, we need to be sure that they really, really are good. Astronomers tend to think, oh, well, it's good enough, about a factor of 2, right? But the factor of 2 doesn't cut it commercially, right? Because if you come back with $15 billion worth of platinum, you probably go bust. You have to know to much better accuracy than astronomers are used to. And that would mean sending out probes to many, many asteroids. So they've got to be very small to be affordable. A whole swarm of microsatellites is what we're thinking of doing. And then you've got to actually mine the asteroid, extract the resources, and there's a lot of problems with that. One is, how do you actually hold on to an asteroid, especially if it's a rubble pile, it just comes away in your hand. So one idea is to put a net around the whole thing to give you something to hold on to. Another problem is that this is what NASA calls an uncooperative body. Right? You're not even no control over it. It's just spinning away. It doesn't even spin on one axis. It kind of wobbles around often. Bad news. And you can see that landing on that is a lot harder than landing on a smooth surface like the moon or something. Not only that, but you can see it's rotating. This one's rotating every few hours. Most of them rotate a bit faster than we would go to. And so you're going from sunlit, very hot, having your mining equipment in the deep sunlight and be very hot, to being in shadow, and you're doing that every few minutes, every half hour, something like that. That means you've got challenging for your design of your equipment. And then mining engineers have to build really rugged equipment, tough, because they have to deal with sudden hard lumps of rock or sudden gaps and mustn't break, and there's loose rubble all over the place that could get in your machinery and has to deal with it. And instead, space engineers, because of that enormous cost to getting things to orbit, have to be very careful. They super design things. They use the high-strength alloys, very expensive, just a right amount of them. Everything worked out to be lightweight and low power. For instance, if you try docking at the International Space Station, right, the standard speed for docking is walking pace, 1 meter per second, like this, right? If you try docking at running pace, you will probably crumple the docking port because it's that tightly engineered. And any mining machine has got to be able to deal with a lot more variation than that. Luckily, the space station itself provides us with a really good test bed to start out some of these techniques, testing some of these techniques in miniature. Right now, the Japanese Kibo module there has the best, the most power, the most space available. But if we decide this is what we want to do, we can send up a much more capable module and attach it. This actually gives the International Space Station a whole new purpose, which is something it's been kind of lacking. Now, later on, we might go a little more crazy and try bringing a small asteroid back from its nice solar orbit and bring it back to an orbit somewhere in the Earth-Moon system, somewhere a long way from the Earth, probably around the Moon, because we want to be a little bit careful here. Don't want to, you know, you've heard of environmental impact statements? Well, this is where we've got to be careful. But it's going to be fine, I assure you. I can tell you why later. It really is. The idea is, it turns out that this isn't completely crazy, and the study we did at Caltech with a lot of very clever guys from JPL, they reckon we can move a 500-ton asteroid, which would be about the size of this room, 5 or 10 meters across, from its orbit into a place we can control it. And this is a really good idea, because it addresses all the motivations I've been talking about. By choosing carbonaceous asteroid, we advance science, love. By learning how to move any asteroid, we bring down the risk, fear. And having an asteroid nearby to work with lets us practice the mining techniques, greed. Also, time is money. Getting out to an asteroid and back, we're paying interest all the way. If it takes a couple of years each way, that's very bad news. So we want to develop much more powerful ion engines than NASA is currently planning to do so. We might even use nuclear-powered ones, because if anywhere is safe to use nuclear power, it's out in space. You just have to be careful coming back. Now, it's not just technology we need, because we can't go far without the lawyers and the diplomats. Now, did you know that owning a celestial body is not allowed under international law? The Outer Space Treaty says no way. It's a common good of mankind. But if you can move it, is it still a celestial body? This is the sort of question lawyers love. In fact, I got a neighbor who teaches Harvard Law who got really excited about this when I told him. Now, scientists and engineers like me, we like to bang our heads against the wall when we hear this kind of stuff. It's horrible for us. But you've got to work these questions out just as much as the technological ones, because you can't have a business where you mine platinum if you can't own the platinum. And of course, the government certainly doesn't have all the skills needed by any means. We need to bring in marketers and economists, i.e. real capitalists, because they have to work on these things. Look at this. This is the price history of platinum over about 10 years, 2000 to 2009. It's horribly fluctuating. It's expensive, but it's fluctuating a lot. Now, unlike gold, though, platinum is not only used in jewelry. It has a technological value. It's used, you may be surprised, in your automobile catalytic converter. And that's a good market, but in the future, platinum might be a key part of the hydrogen fuel cells, which may power all vehicles in the future. But we don't know. We need analysis from marketing people. Also, if we bring back too much platinum too quickly, we might depress the market and turn our profit into a loss. And that really wouldn't be good. So now, economics is not my strong point. You may not have realized it, but I didn't go into astrophysics for the money. I could use some help. All right. All of this mining, though, will be done robotically. And even if we're making piles of cash from space mining, none of this seems to get humans out there where we space cadets would like them to be. Not all of them. Now, this mining will promote humans in near space, the Earth-Moon system, because we want to make those scientific measurements and we want to practice our mining techniques. And as costs come down, space hotels will become affordable. And this is actually not a joke. This guy is really trying to build these. But can asteroid mining take people out into the solar system? Okay, well, not at first. But if we think a little way down the road, it does. Once we're making a lot of money from space, sending people will become cheaper. And then we're going to need a space geek squad. Because if you get a pebble wedged in your billion-dollar mining robot, that would be irritating. And we'll have to send out a repair crew. You can tell where I first gave this talk. And to fix them up, fix up your robot and refuel them and send them on to make yet more money at another asteroid. Another thing we're going to need are space sheriffs. We're going to need space sheriffs because a good asteroid is hard to find. So these rare platinum-rich asteroids will be really hot property. And space pirates could move your asteroid into an orbit they know, but you don't. And space is big. Who knows where it's gone? And even if you find it again, how do you prove it's yours? Right? So we're going to need space sheriffs to sort them out. Like this is an early Sean Connery playing a sheriff on a mining colony of one of Jupiter's moons. So almost right. Pretty good. Long term, what's going to happen is the tailings are going to be important. Huge piles of tailings, mainly composed of ultra-pure iron, are going to be sitting up there after we've mined in space. And in space, they're valuable. It's no use bringing iron back to Earth, that's too cheap. But iron in high orbit around the Earth is worth a lot. And I think the first use might actually be to build solar power stations, not to send power back to Earth, but to help in the mining operation. So I think now we can see how mining asteroids will create a space economy, but will also require human spaceflight to stretch well beyond Earth orbit. And once we go to the main belt for asteroid resources, we'll pass Mars on the way there. And so stopping off to land on Mars will become relatively straightforward. To get there, to get started, we have a problem though. America's space program is facing an existential crisis, and this has become a very sad image of a children's book I saw just last Christmas. This is things that don't fly. If NASA fails to find a compelling reason for its existence in the next few years, I think it could wither away and have its remaining functions divided up among the other agencies. The end of the space shuttle program has a lot of people asking why we pay for a space program. The human program feels stuck. Why do we have that International Space Station? Why don't we even have our own rocket for lifting people into orbit? And why haven't we gone anywhere? So there is an answer. We should go to the asteroids in a quest of love, out of fear, and for greed. And NASA should take the lead in enabling all this. NASA's goal should not be human exploration. It should be enabling the harnessing of the resources of the solar system. And human exploration will just follow naturally. From Lewis and Clark to the Golden Spike that completed the Transcontinental Railroad was just 65 years. So the West went from being unexplored, quote, wilderness to an integral part of the US economy in 2 generations. I believe we're now at the Lewis and Clark moment for opening up the solar system, and the US government can play the same role there as it did in the West, buying down the risk for the pioneers. And then, by making space part of the US economy, leveraging our greed, we can deal with our fear, we can retire the risk of a Tunguska-like impact wiping out Washington, D.C. or any other metro area. And what of love? Oh, I missed that one. What of love? Well, greed will teach us to work in space on a whole new scale, and the profits from space will lower the costs. And that means that new generations of greater observatories in space will be affordable, and human exploration of the solar system will get started for real. And what will our curiosity, our love of finding things out, then discover? Thank you.